Welcome to the deep dive. Today we're diving into a paper.
Oh, cool.
Yeah, it's titled SurVAE Flows, Surjections to Bridge the Gap Between VAEs and Flows.
Okay.
And it's all about generative models. Really gets into how to merge VAEs and normalizing flows.
Huh. Interesting.
Yeah, so, I mean, I think our listeners are pretty familiar with this area.
Yeah, they're experts.
Exactly. So we can kind of skip the basics and jump right into the good stuff.
Sounds good.
So what's the core challenge this paper's tackling?
Well, it's kind of like this, right? You have normalizing flows, super good at exact likelihood calculations.
Right.
But they don't really handle changes in data dimensionality well.
And then on the other hand,
Yeah.
you've got VAEs, really good with dimensionality changes,
Yeah, they are.
but they rely on those lower bound likelihood estimates.
Exactly. So this paper wants to bring those two strengths together.
Okay, so how do they propose to do that?
Well, they lay out this framework, right? It breaks down transformations into three parts. Forward transformation, inverse transformation, and likelihood contribution.
And this is how they build their models.
Yeah. This is the foundation. And then they introduced this really cool idea called surjections.
Okay, surjections.
Yeah. So these transformations are deterministic in one direction, but stochastic in the other.
Okay, so what does that mean for the model?
Well, it means you can have both. The exact likelihood computation, and you can manipulate dimensionality.
Oh, so they're kind of getting the best of both worlds.
Exactly.
So how does this actually work in practice? Could you give us an example?
Sure. So there are actually two types of these surjections.
Okay.
Generative surjections, those are surjective from latent to observed space.
Makes sense.
And then inference surjections, which are the reverse. Surjective from observed to latent space.
Got it.
And they have some cool examples in the paper, like tensor slicing.
Oh, I heard of that.
Yeah. Really efficient way to reduce dimensionality.
So you're basically getting rid of some dimensions, but keeping the important information.
Exactly. And then there's another one, rounding, which is basically dequantization.
Oh, right. Making that discrete data continuous.
Yep. You add some uniform noise, round the result, and boom, continuous data. Ready for flow models.
That's clever. So it seems like they're addressing a real limitation of flow models there.
Yeah. It's a pretty powerful toolkit they're building.
And what about other layers? Do they come up with any new SurVAE layers?
Oh, yeah, tons. Like the AB surjection.
Oh.
It's super useful for modeling data that has symmetries.
Oh, interesting. How does that work?
Well, it basically folds the data space along those lines of symmetry. So the model can represent those distributions in a more compact way.
Makes sense.
And then there's the max surjection.
Okay.
It uses, max pooling.
Oh, yeah, from convolutional neural networks.
Right. And here it acts as a downsampling layer.
So it's basically reducing the dimensionality of the data.
Exactly.
This is really cool stuff. But how does all of this connect to, like, existing research on generative models?
Well, that's one of the most amazing things about this framework.
Yeah.
It really brings a lot of different models together.
Oh, wow.
Like VAEs and probabilistic PCA.
Yeah.
You can see them as using stochastic transformations within this framework.
Interesting.
And even diffusion models.
What a great...
Yeah, they fit right in as a special case of SurVAE Flows.
Huh. I wouldn't have guessed that.
That's pretty cool. And then you have all these models that use surjective transformations.
Like what?
Well, there's dequantization, V-flow, ANFs, CIFs, discretely indexed flows.
Oh.
Slow down.
Sorry.
That's a lot.
Yeah, and deep TMMs and R8 flows, too. The point is, they can all be viewed through this SurVAE Flows lens.
So it's like a new way of thinking about generative modeling altogether.
Yeah, exactly.
So it sounds like they've laid out a really solid theoretical foundation.
They really have.
But how does it perform in practice?
Oh, that's what we'll dive into next time. They got some great results across different data sets. Awesome. Can't wait to hear more about that. Okay, so let's dive into those experimental results.
Right.
You mentioned last time that they had some success with synthetic data.
Right.
What kind of synthetic data were they using?
So they created these data sets that had built-in symmetries.
Okay.
Like, distributions that are invariant to reflections or rotations.
So if you flip it or turn it, it looks the same.
Exactly. And those can be tough for normal flow models to capture efficiently.
Yeah, that makes sense.
But they showed that with SurVAE flows, specifically using the ABS surjection layer, they could model these symmetric data sets really well.
And that AB surjection layer, that's the one that folds the data space.
Yeah. It takes advantage of that symmetry to make the representations more compact.
Really clever.
It is.
And then you mentioned they had some impressive results on spatial MNIST.
Oh, yeah.
That's the point cloud version of MNIST, right?
Yeah.
So how did they approach modeling that kind of data?
Well, point cloud data has this special property. It's called permutation invariance.
Permutation invariance.
Yeah, it basically means the order of the points in the cloud doesn't matter.
Oh, right, because it's just a collection of points in space.
Exactly. So they came up with 2 ways to handle that within the SurVAE Flows framework.
Okay, what are the 2 ways?
So the first one they call sort flow.
Sort flow.
Yeah. Basically, they sort the input point cloud before feeding it to the model.
So they're imposing an order on the data.
Exactly. That way, they get rid of the permutation ambiguity,
Makes sense.
and then they use a stack of coupling flows to model the sorted data.
Coupling flows, those are those bijective transformations.
Yep. And they parameterize those flows with transformer networks.
Okay, so that's one approach. What's the second one?
The second one's called permute flow.
Permute flow.
And this one is really cool.
Okay.
Instead of sorting the data first,
Uh-huh.
they add these stochastic permutations between the coupling layers of the flow model.
So they're shuffling the points randomly.
Exactly. And they do this during training, so at each step, the order's different.
Wow.
So the model is forced to learn representations that are invariant to the order of the points.
That's really elegant.
It is.
So which strategy worked better?
Well, it turns out permute flow actually outperformed sort flow on spatial MNIST.
Interesting. So directly incorporating the permutation invariance was more effective.
Yeah, it seems that way. And actually, permute flow achieved state-of-the-art performance.
Real?
Yeah. Among non-autoregressive models, at least.
That's super impressive.
It is.
Okay, so we've talked about synthetic data, we've talked about point cloud data.
Right.
What about image data? You mentioned they use max pooling as a downsampling layer.
Yeah. So remember how I said max pooling is usually used in convolutional neural networks?
Yeah, for downsampling and feature extraction.
Right. So they wanted to see if they could use it in SurVAE flows, too.
Instead of the usual tensor slicing.
Exactly. So with tensor slicing, you're just throwing away some of the data to reduce the dimensions.
No.
But with max pooling, you're keeping some information about the parts you're discarding.
Because you're selecting the maximum value.
Yeah, exactly. So it's a bit more sophisticated.
So it's like a more informed way of downsampling.
That's a good way to put it.
So what happened when they tried it?
Well, it's kind of interesting.
Yeah.
They found that using max pooling actually led to slightly worse log likelihood scores.
Oh, really?
Yeah, compared to tensor slicing. But here's the thing.
What?
The generated images using max pooling looked better.
What do you mean looked better?
They had better visual quality.
So even though the likelihood was lower, the images were more realistic.
Yeah, exactly. They measured this using the inception score and FID.
So, right, those metrics that try to capture perceptual quality?
Yep.
So it's like there's a trade-off between how well the model fits the data and how good the generated samples look.
That's what it seems like.
Good
And
idea.
it suggests that max pooling might be better at capturing those higher level features.
The ones that are important for how we perceive images?
Exactly, even if it means the likelihood takes a little hit.
Fascinating. So it's like they've uncovered this new design consideration for generative models.
Totally. They've given us a new way to think about these trade-offs.
Okay, so we've seen some really interesting results.
Yeah, we have.
I think it's time to wrap up and summarize what we've learned from this paper.
Sounds good to me.
Okay, so we've gone pretty deep into SurVAE flows.
Yeah, we've covered a lot.
Let's try to, summarize the key takeaways.
Sure.
What makes this paper so important for generative modeling?
Well, I think the biggest thing is that unified framework.
Right, connecting VAEs and normalizing flows.
Exactly. Bringing those two together with the idea of surjections.
Those deterministic in one direction, but stochastic in the other transformations.
Yeah. And that leads to models that can handle both exact likelihoods and changes in dimensionality.
And of course, they also introduced all those new SurVAE layers.
Oh, yeah, those were cool.
Can you remind us of a few of those?
Sure. So there's the surjection layer, right? For modeling data with symmetries.
Right, making those representations more compact.
Exactly. And then the max surjection layer using max pooling for downsampling.
Oh yeah, that was interesting.
And then we had the sort surjection layer for dealing with sorted data and exchangeable models.
Uh-huh.
And finally, the stochastic permutation layer for enforcing permutation invariance.
So they really showed how versatile this framework is.
Yeah, definitely.
And their experiments really backed it up.
For sure. State-of-the-art performance on point cloud data.
And some intriguing findings for image generation.
It really makes you think differently about generative modeling.
It does.
Yeah.
So what are the broader implications here?
Well, I think it opens up a whole new way of looking at generative models,
Okay.
encouraging us to think beyond just those traditional bijective transformations.
So looking at those non-bijective transformations more closely,
Exactly. There's so much to explore there.
and it could have implications beyond just
But
generative modeling, right?
absolutely. Think about unsupervised learning.
Yeah. If we can learn better representations of data using these non-bijective transformations,
That could be huge.
this paper really lays the groundwork for some exciting future research.
I totally agree. It's a real game changer.
So to all our listeners out there, if you're interested in generative modeling or unsupervised learning,
Check out this paper,
it's definitely worth a read.
and who knows, maybe you'll be the one to make the next breakthrough.
Thanks for joining us on this deep dive into SurVAE Flows.
It's been a pleasure.
We'll see you next time.